Hey folks! Well, now that we've covered regular expressions for scanning or tokenizing, we want to go through and look at context-free grammars and the establishment of the basic structure of our program, the syntactic structure. So, that's where we'll go for this one. Essentially, for our context-free grammar, we want to go through and describe all the valid ways in which a program can be described as sequences of token types. So what are the different kind of orders of tokens that form a valid program under the language? And again, ignoring some of the semantic aspects for now, just focusing on purely the syntactic structure. So things like, the rules for variable declarations, it has to be, a data type identifier, semicolon, or something like that. So what we'll do is we'll come up with a set of grammar rules that say, okay, for each component, here's what it can be made up of. And what it can be made up of is typically other component types or tokens. So I might have something that says a program can consist of the keyword begin, an open curly bracket, a list of statements, and then a closing curly bracket. So I might use tokens for the begin and the open and close or curly brackets, but then I'd have some kind of a component description that said, okay, a list of statements. And a list of statements, I might say, can be defined or can be composed of a statement followed by a list of statements, or it can be composed of just a single statement. And so we start describing things in terms of what the components might be, and some of those might be sort of abstract components. So ultimately, we might say something like a statement could be a variable declaration. And a variable declaration is composed of, again, let's say an identifier, or pardon me, a data type, an identifier, and a semicolon. So we'll describe things in terms of this hierarchy of rules and abstract components and tokens. All right, and I'm going to use kind of a Yaki-like syntax for the context-free grammars here, since we're going to be looking at Yak later on as well. So the basic rule format is going to be, we'll describe a component, a colon, and then what that component is made up of, and then a semicolon to end it. So each rule will start off with the name of one of these abstract components that's made of other things, and will end with a semicolon. So for instance, if we have already tokenized our code, and we've decided that we have tokens to represent identifiers, to represent integers and chars and floats, and a token to represent a semicolon, then we might have a rule that says, okay, well, one of the components that we're interested in is a data type. And we might say a data type can be either a char or an int or a float. So I'd have rules for those. I could say a data type could be a char. I could have another rule that said a data type could be an int. Another rule that said a data type could be a float. So again, we've got our kind of abstract component, and then the specific pieces it's made up of, and a semicolon to end it. And again, components can be built up of other components. So I might say that a variable declaration is made up of a data type, followed by an identifier, followed by a semicolon. And again, an actual semicolon to end our rule. So we're describing pieces of our language in terms of other pieces of the language and specific tokens. All right, now the syntax there can get a little lengthy. If I've got this kind of long sequence of rules, it would be nice if I could simply say, instead of having these three separate rules, saying a data type could be a char, a data type could be an int, a data type could be a float, it would be nice if I could say a data type could be a char or an int or a float. And so there is a syntax that we'll use for that, and we'll use the vertical bar, the pipe, to represent or. So I could say a data type could be a char or an int or a float, and then end my rule. So that's essentially just a compact way of saying the same thing. All right, in terms of this idea of sort of abstract components, I'll sometimes refer to them as non-terminals. So these are, again, abstract things that are built up of other things. right? Sequences of other non-terminals, other abstract components with some tokens sprinkled in. So it does give you a way to describe things like a loop, a function declaration, a variable declaration, which of course could be composed of a whole bunch of different possible combinations of different things. Usually you'll have one sort of top level generic component, generic abstract component to describe a program as a whole. You can use any name you like for that. So you might decide I'm going to use the name program as my top level abstract non-terminal, or start, or top level, or whatever it might be. Pick a name to represent that most abstract level of your the programs you're trying to describe. And then the set of grammar rules that we come up with have to provide a set of rules that gives you a valid way to build any valid program in the language. So there's got to be, for any program that you want to be valid in the language, there's got to be some way to express that using your combination of rules. All right, so let's take a simple language as an example. So in this made-up language of ours, we'll have identifiers that can be just a sequence of alphabetic characters. We'll have positive integers in the language, so just one or more digits. We'll have an assignment operator that's just the equal sign. We'll have the keywords begin and end. We'll have a plus operator, and we'll have a period. And those will be the tokens that we'll use in the language. I'm going to assume for the time being that we come up with a regular expression for each so that our tokenizer can go off and read the source code and figure out which combinations of characters are which tokens. And then our context-free grammar is going to use a name for each of the different token types. So we might use the name identifier, an integer, and a sign, and begin, and end, and plus, and stop as the names for those different types of tokens. So for our language rules, let's say that programs in the language have to begin with the word begin, have to start with the word begin, have to finish with the word end, and they can have one or more assignment statements inside. And each assignment statement looks like an identifier, an equal sign, and then an expression, and then a period. Our expressions can either be just integers, just identifiers, or an expression plus an expression. Right? So you get this kind of recursive definition of what an expression could be, so that eventually you could build up something like a valid expression might be x plus 3 plus y plus 17 plus 204 plus foo. So this is kind of our informal description of what the rules of the language would be, and we'll see if we can come up with a reasonable grammar for this. So for example, a valid program might be something like begin, x equals 27, a period, and an end. Right? So we've got our begin and our end, we've got a single assignment statement. Or we might have multiple assignment statements, right? Each that's got an identifier, an equal sign, an expression, and then the period. Right? And here our expression is one of those combination ones where we've got an integer plus an identifier plus an integer. So for our rule set, we'll quite often create our grammar rules sort of starting from that most generic, most abstract term. So let's use program as our top level non-terminal. I'll use assign statement as the name for an assignment statement. I'll use expression as the non-terminal for an expression. So we'll describe how each of these three abstract pieces can be built up out of other pieces and tokens. Now, we did say that our program was supposed to support multiple assignment statements. So I'll need another layer in here that says, okay, well, I've got something that describes a single assignment statement. Maybe I'll have one more that describes a bunch of them. So I'm going to use statement list as the non-terminal name for a whole series of assignment statements. So our program would be described as a begin, followed by one or more statements, followed by an end. Right? So I could come up with that in terms of a rule. Oops, I'm missing my semicolon on the end here. So a program has a begin at the beginning, so that's the token, a statement list, and then an end And then I should have a semicolon here to end my rule. And again, that statement list is one or more statements. So now I need a way to describe what that statement list is made up of. So a statement list could be either just a single statement or a bunch of them. So I could describe that as saying a statement list can be a single assignment statement, or it can be a single assignment statement followed by a statement list. And that, of course, could be one or more statements. And again, I'm missing my semicolons on the end here. So there should really be a semicolon there if I'm following my Yaki type syntax. So now we need a way to describe an assignment statement. Right? Let's say an assignment statement is an identifier, the assignment operator. So again, those are our two token types, an expression, and then a stop token, which was the period. Right? So now we need to figure out what a good rule for an expression would be. So maybe I can say that an expression could be just an identifier by itself, or just an integer by itself, or it could be two things added together. So it could be an expression plus another expression. Right? So this way I can build up, I can have either just a single thing, or I can have this series of operators and expressions, which eventually these things will each boil down to either identifiers or integers with pluses in between all of them. Right? So we can come up with a rule set to describe how to build things in the language. And essentially any program that follows those rules, any program that can be built out of those rules, is a valid program in the language as far as our grammar is concerned. So the whole list here, minus the, or missing the semicolons again, is a program, right? It can be begin, statement list, end. The statement list is a single statement, a single assignment statement, or an assignment statement followed by a list of others. An assignment statement is an identifier, an assignment operator, an expression, and a stop token. And then an expression is either an identifier, an integer, or an expression plus an expression. Now, in fact, this is an ambiguous grammar, but we'll get into that later. So, if I want to see if a particular program is valid, so somebody gives me a source code program that's supposedly written in this language, and I want to see if it's actually valid, then I have to see if there's a way that I can produce that program using this set of grammar rules. So to derive that program using this set of grammar rules. If we can't generate the program using our grammar rules, then it's not a valid program as far as our grammar rules are concerned. So if we can generate the program using those grammar rules, then essentially the order that we apply the rules in tells us what the components of the program are and gives us a bit of an idea of what the structure of the overall program is. So let's take a look at an example. Let's say we've got that first case that we did where we said we had a begin, an assignment statement, and an end, right, where it's x is 27. So if we were going to go through a derivation to see if we could produce that program, then we'd say, okay, well, we start with that generic abstract top level one program and see what we can turn it into. Well, obviously we need to turn that into a begin, a list of statements, and an end. Right? That's the only rule we have available for program. So the begin kind of matches that begin token, the end will match the end token. We need the statement list in the middle to eventually match this x equals 27. So out of the rules available, we can either have statement list goes to an assignment statement followed by a statement list, which would mean more statements. Clearly that doesn't apply because we've only got the one statement. So we use this rule. The statement list goes to an assignment statement. And then we want to see if an assignment statement can produce this, the x equals 27, which of course it can. Right? We've got that assignment statement goes to identifier, which matches the x, assign, which is going to match the equals, integer, which is going to match the 27, and stop, which is going to match the period. So we've got a derivation that'll work. And again, this assumes that somewhere off there we've got our tokenizing regular expressions that match x with an identifier and 27 with an integer and equals with an assignment and stop with a period. All right, say we've got another one. This time we'll make it a series of assignment statements inside the program and a more complex expression. So again, same sort of idea. We start with program, program, oh my goodness, I apparently took a shortcut here and left off the begin and the end. So program goes to begin, statement list, end, and the begin and end match these beasties. The statement list is the one that we need to match these two statements. So this time we want the statement list to go to an assignment statement followed by a statement list. So we want that first assignment to match foo equals 123, and then that second statement list we need to apply the rule that says, okay, statement list goes to an assignment statement. So that second one will match our second assignment statement. Right, and then as we were plowing along, we'd say that first assignment statement has the form identifier, assign, expression, stop, where we've got just the integer. So there, that first one, we've got the foo equals 123. Right, so our expression just simply goes to an integer, the 123. And then for the second one, we've got that more complex expression. So we've got an assignment statement, goes to identifier, assign, expression, stop, where that expression has eventually got to match this 17 plus foo plus 100. So just arbitrarily resolving those different expressions, we can say an expression goes to an integer. So that first expression goes to, let's say, the integer 17, and then the plus would match the plus right after that. So it would match this plus, and so we've still got the foo plus 100 to deal with. And so we could say that that second expression goes to an expression plus an expression, which are going to match the foo and the 100. Now there are actually different ways that we could derive, that we could use our set of rules to derive that particular program. So this is actually an ambiguous grammar, but we'll get to that in a bit. So it's sometimes a little clearer if we represent our derivation as a tree, where we say our top level program is made up of a begin, a statement list, and an end. That statement list is made up of one assignment followed by a statement list, and that second statement list is essentially made up of our second assignment statement. Right, so that first assignment statement is an identifier, the foo, followed by an assign, right, the equals, followed by an expression, that's an integer, that's the 123, followed by a stop, period. And then our second assignment statement is an identifier, the x, followed by an assign, the equals, followed by an expression that we'll talk about in a sec, followed by a stop, right? And that expression has got to work out to the 17 plus foo plus 100. So that could be made up of an expression, which is the 17, and then a plus, and then an expression, which is going to be an expression plus an expression, right, to get the foo plus 100. So you can draw your derivation out as a tree to make things a little bit more visually clear. And sometimes from a human perspective, again, this can be a more obvious way to figure out your derivation without making a mistake. Now, if there's more than one way to generate a particular program under the grammar, then there's multiple possible interpretations of what the program is, and the grammar is called ambiguous. It's generally not a good thing. Essentially, if there's two possible derivations, two possible different structures to a program under the grammar, then if you built two different compilers, one compiler might say, oh, well, this is obviously the derivation I should be using, and the other compiler might say, this is the derivation I should be using, and when you compile your program under one, it's going to behave differently than when you compile a program under another, because they think the program has different structures. So ambiguous grammars are an issue as far as we're concerned. We want an unambiguous grammar to describe our language. So just as an example, for that particular grammar that we had, we'll show that we can produce two different trees, two different syntax trees, two different parse trees, showing two different structures for the program. So the difference is going to come in with that with the structure of this second expression. So we'll find two different derivations that show two very different structures for what this expression means, so to speak, under the two different derivations. So we have that one version where we said that our expression had essentially 17 plus some other expression that was the foo plus 100. So you want to think of this in terms of order of operations. This is kind of like saying we're doing 17 plus all of this. So it's kind of saying we're implicitly bracketing our foo plus 100. These two things belong together, and the result of this foo plus 100 is getting added to the 17. If we can come up with a different derivation with a different structure here, it might imply a different order of operations, which of course is exactly what we're going to do. So we'll show a different derivation. This was our first derivation for that expression. We said it was, we expanded that first expression to an integer to 17 plus a second expression that in turn is an expression plus an expression. Right, so we get our foo plus 100. The alternative is to say, okay, well, we've got this expression that turns into an expression plus an expression. This time we'll say the second one is just the 100. Right, so we'll apply the rule that says, I'll expand that expression to just an integer that's just a 100. And the first one, we'll apply the rule expression plus expression. So this expression is an expression plus an expression, where the first part of it is the 17 and the second part of it is the foo. So this kind of implies that under the first derivation, we're saying this is 17 plus foo plus 100, whereas for the second one, this is saying 17 plus foo plus 100. I guess with typical addition, this doesn't really matter, but suppose it was a subtraction operation or a division operation or something like that, it would make a significant difference. So we want the grammar that we pick to guarantee there is only one possible parse tree for any valid program in the language. So there is only one possible way to interpret any given program in the language. So in terms of eliminating ambiguity, we want to get rid of the places where you could apply a rule to either side and get the same result, right? Get a valid derivation, that is. So this place where we had in our original set an expression can be replaced by an expression plus an expression. What we'll do instead is say we'll have one side of this, instead of being expression followed by expression, we'll have one side of this turn into a different kind of non-terminal. And that different kind of non-terminal will not allow pluses inside of it. So we've got to go through and evaluate all of the pluses first, for instance, using this rule, and a different rule to evaluate the other side. So, as an example, we could replace that rule, our expression goes to expression plus expression, with something like this. An expression can be either an expression plus an integer, or an expression can be an expression plus an identifier. Now we've already decided those are token types, right? Integer and identifier. So there's no way, if I apply this rule, then it's saying this can match something and then a plus and then an integer, but there can't be anything after it. And this can match an expression plus and then an identifier, but there can't be anything after that. So effectively, these things have to evaluate the last plus in an expression. So the only way, if we're looking at, say, foo plus 3 plus x, the only way that can match is if we say this one can only match an expression that ends in an integer. Foo plus 3 plus x doesn't end in an integer, so that one can't apply. This one can only match cases where it's an expression plus some identifier. Here we've got that. We've got some expression plus an identifier. So it would have to apply this second version of the rule and say, okay, this expression matches an expression plus an identifier where we've got a plus and an x. There's no alternative way that we could derive through this process. And then for that second one, now this expression has to somehow wind up matching foo plus 3. So it's going to look at that and say, okay, well, for a foo plus 3, that's got to be an expression plus an integer. So it applies that rule, expression plus integer. The plus goes to the plus, the integer goes to 3, and the expression goes to an identifier, goes to foo. So this way we can eliminate the ambiguity that we get in expressions like this. Now, our grammar rules also determine the order of operations. So it's going to impact both associativity and precedence. So the grammar rules that we pick have to reflect the order of operations that we want to apply in our language. So if I do something like expression plus integer, like we just did in this previous example, then it's saying that the first rule that I apply to my kind of top level expression has to say this plus and the integer happens at the top of the tree, if you like, and the rest of the expression is evaluated further down, like we did in this particular case, where we've got an expression goes to a plus and an identifier, and the rest of this stuff is buried deeper in the tree. So this is effectively saying that this stuff, the foo plus 3, is evaluated and then added with the result, or added with that identifier. So this is essentially saying that the plus on the right-hand side is evaluated last, right? If I've got something like this, foo plus 3 plus x, that second x, or second plus, is evaluated last. So this is essentially saying that the stuff that's buried deeper in the tree is going to get evaluated first, which means, in this case, that our plus operators get evaluated from left to right, which is usually what we want for an addition operator. Right? So this is basically going through and saying, if I take this approach and I say my expression can go to an expression plus and then some token, then I'm guaranteeing that I've got to go through in the tree and do the evaluation of the rest of the expression first, if you like. So this is a way of determining the order of operations. If I say expression plus and then a token, for instance, then I'm saying that the expression on the left-hand side is going to be deeper in the tree, and whatever's on the right-hand side is going to be higher in the tree, and essentially saying that we're evaluating left to right. If we flipped it around and we said that instead our expression rule was an expression goes to an integer plus an expression, that would be implying that we do something like 3 plus and whatever the rest of the expression is at the top level of the tree, and the rest of the expression deeper down, which would mean the leftmost plus gets evaluated last. Right? The stuff higher in the tree gets evaluated last. The stuff deeper in the tree gets evaluated first. So the order of evaluation, if you like, is the opposite to the order of derivation. So the derivation rules that we apply at the top of the tree are going to equate to things that we actually evaluate in the program last. All right, so again, we want higher precedence operations to be lower in the derivation tree so that they get evaluated first. They get derived last, get evaluated first. So for something like x equals, or an expression that was x plus y times z, usually what we want is for this to go through and do the plus. We want the y times z operation first and the plus to get applied afterwards. So in the derivation, we're going to do the derivation that gets the plus first and the derivation that gets the times last. So you're just thinking that your order of derivation is the opposite to your order of evaluation. Now, again, to get this effect, we can go through and create a hierarchy of non-terminals where we'll go through and derive the low precedence non-terminals first and the high precedence non-terminals later. So let's say we decide that we'll have two expression types, one for addition expressions and one for multiplication expressions. And so we'll make sure that we do the add expressions first in the derivation process, so they're higher in the tree, so they get evaluated last. So I could say that a generic expression goes to an add expression, where an add expression can be an add expression plus a multiplication expression. Why have I got two versions of add expression plus multiple expression? I think we've just got a duplicated line there that's unnecessary. So an add expression can go to an add expression plus a multiplication expression, or it can go directly to a multiplication expression. So this way, if I've got something like x plus y times z, this is saying we'll get the, or let's say a plus b plus y times z, for instance, we'll get the pluses at the top level, and then later on, deeper in the tree, we'll get the y times z. All right. So we get our low precedence operators first, and then once we're done with all the low precedence operators, we move on to the high precedence operators. So there's no way for a multiplication expression to give you back a plus operator. So deal with all the pluses first in the derivation, and then deal with all the multiplications. And then for the multiplication operations, we can say, okay, those can either go to a multiplication operation, a multiplication operator, and then a simple data type, or just a simple data type. So this way, here we get all of the multiplication operations piled on, and eventually get our simple values, say our integers or our identifiers, as the final components. So an expression in terms of order of precedence goes through our add expression, or order of derivation rather, goes through our add expressions, and then our multiplication expressions, and then to the simple data types and gives you something specific. So if somebody gave you an expression that was just 17, for instance, then you can still derive that. You can say, okay, well, it goes to an add expression, goes to a multiplication expression, goes to a simple, goes to just an integer. Or if somebody gave you an expression that was just an x, right, you'd say that's an expression, goes to an add, goes to a mult, goes to a simple, goes to an identifier. Or if somebody said you had an expression like x plus y, then you're saying, okay, well, my expression goes to an add expression, there's no pluses in it, so it goes straight to a mult expression, which is going to go to a mult expression times something simple. So that gives me my one multiplication and the identifier on the end, and then this mult expression would go to a simple and my other identifier. Right? So you can go through this way and guarantee the order of operations and the precedence of your operations. So again, if we had this set of rules and we had a fairly, well, relatively lengthy statement, so we've got v plus w times x times y plus z. Again, we want those multiplications deep down in the tree, and we want those pluses up top, and we want the pluses to evaluate left to right. So in this particular case, under our rules, an add expression can go to an add expression plus a multiplication expression, or just a multiplication expression. Well, we've got lots of operators in here, so it can't, or we've got a bunch of plus operators, so it can't go to just a multiplication expression. So we've got to use the rule that says, okay, well, it must go to an add expression plus a multiplication expression. Now, once you've got a multiplication expression, there's no way to get back to a plus. So this thing, this plus, has to be that last plus in the expression, which means that this thing must eventually go down to our z. So this is going to get our plus z as this kind of last part of the last two steps of this top level of the derivation. So we've got that plus at the top, and then this add expression has to represent all the rest of this stuff, the v plus w times x times y. So again, this can't go to just a multiplication expression because we've still got a plus in there. So it's got to go to add expression plus multiplication expression. Well, there's only one plus in here, So that's got to match, that plus has got to match that plus, which means that the add expression on the left has got to wind up matching the v, right? It's got to go down to a multiplication expression, to a simple, to an identifier. And this multiplication expression has got to eventually match our w times x times y. So again, this thing has to match a multiplication expression. It can't just go to a simple because we've got multiple operators in there. So it's got to go to a multiplication expression times some simple. So that simple can only be that thing on the end. Right? So it's got to go to our y, which means that this multiplication has to match this one, which means that the multiplication expression deeper down has to be that first one, the w times x. So again, we've got this multiplication expression goes to a mult expression times a simple, which can only be the x, and then that first multiplication expression can only be a simple, which can only be the w. So there's only one possible derivation tree to get this. And if we see it, if we look at what we've got here, we're saying, okay, here we've got w times x times y plus v plus the z. So we actually get the order of operations that we want as well. So we can wind up coming up with a set of grammar rules that give us the associativity and the precedence rules that we want. If we decide that we want to go in and say, well, I want to be able to parenthesize as well so that I can get different orders of evaluation if I need to, then they are essentially the highest precedence that we're interested in. So they have to be, if you like, at the lowest level of our derivation process, the bottom of the tree, if you like. So for that, we could take that simple rule that we had earlier and say a simple can be either an integer or an identifier or an expression in brackets. And that way, we could boil through and get this as higher precedence, lower in the tree than the other operators. So we can go through and gradually build up a detailed grammar for exactly the operations that we want and exactly the order of operations that we want. But it does involve some careful thinking about what this winds up looking like. So if you're ever interested, you can go through and see the tokenization for the C programming language. So it's available here, and it's a couple hundred lines of Lex grammar rules specifying how to tokenize things. And you can see the parsing rules. And this is the one that might be particularly interesting because it does go through and show you the different layers of non-terminals used for all of the different operators in C to guarantee that you get the right precedence and the right associativity for all of them. So again, there are hundreds of rules in this, but it's interesting to walk through, and you can see how C actually gets parsed using a grammar like this. So I would highly recommend having a boo through this if you're ever trying to figure out how things work in parsing, especially in the next little while as we get into looking at Lex and looking at Yak. You can actually get some good ideas on how to approach things by going through these grammars. All right, well, that was a rather lengthy session, but we'll leave it there.